Hi Bobcats. In this video, we're going to put together the concept of formation reactions and Hess's law to create a way to calculate the delta H for any reaction from heats of formation data. So why are we introducing the concept of formation reactions? We can combine the concept of formation reactions and Hess's law to come up with a way to calculate delta H of any reaction from a limited set of tabulated heat of formation data. So we don't have to tabulate the delta H for any possible reaction as long as we have the heat of formation data for all of the reactants and products. Remember, Hess's law works because enthalpy changes are a state function, which means it doesn't matter if we do the reaction in just a single step, the way we tend to write reactions, or if that reaction actually takes place as a series of steps, as long as that series adds up to give us the overall reaction. So the cool thing about Hess's law and formation reactions is that all of those elements that we write on the reactant side of formation reactions will simply cancel out, so we only have to deal with our desired reactants and products. The equation we're going to wind up with says that the delta H for reaction is given by the product of the coefficients in the balanced equation times the heats of formation for all of the products. And then we're going to add that up for all of the products. We're going to repeat that process for the reactants. We're going to take their coefficients times the heats of formation for all of the reactants. Then we're going to add all of that up. Then we're going to take the sum we created for the reactants and subtract it from the sum for the products. This equation is something that I'll refer to as the granddaddy equation. That's something I picked up in a conference on teaching chemistry a long time ago. So when I talk about the granddaddy equation, this is the process that I mean. So I'm going to try to show you where this really strange looking equation comes from. So if we need to calculate delta H for the reaction of ethylene, which is C2H4, this is not quite an alkane. It doesn't have enough hydrogens, but the prefix F for 2 carbons still hold. And so this chemical over here on the reactant side is called ethylene. So we're going to react ethylene with 2 waters to make 2 methanols. So here are 2 methanols. Notice there's just 1 carbon in this compound, which is where that meth prefix comes from. So we're asked to find delta H for this overall reaction, and we're given, along with it, the heats of formation for each of the reactants and products. So we need to try to use Hess's law to add up the given heats of formation to get delta H for this overall reaction. And because all of the elements are going to cancel out, I'm going to ignore everything that's on the reactant side of these 3 reactions that we have data for and focus just on the product side. So for instance, we have over here on the product side, we have 2 methanols. And so the first formation reaction is for the formation of methanol, but it only has a coefficient of 1. So we're going to need to double this reaction. We multiply all the coefficients by 2. We also have to multiply the delta H by 2. That's what I'm showing down below. For our reactants in our target reaction, let me switch colors here to red. For the ethylene is going to appear on the reactant side, and it has a coefficient of 1. When we look at our second formation reaction, ethylene does have a coefficient of 1, but it appears on the product side. So when we move it to the reactant side and basically flip reactants and products, we have to change the sign of delta H. And so that's what we'll record next down here at the bottom. We just took that second formation reaction and flipped it around. And when we flipped it around, we had to change the sign on our delta H. So we wound up with a negative sign right there. For our third reaction, we are given the heat of formation of water. Well, water in our target reaction appears on the reactant side, and it has a coefficient of 2. So we need to manipulate this equation to have a coefficient of 2 and to reverse our reactants and products. Okay, on this slide, I took the manipulated equations that we had on the previous slide. So these are the three equations that we had made sure the coefficients were right, and then some of them we had flipped, and so consequently we had to do things to the delta H values. So we had to multiply this one by 2, and we had to multiply this one by 2, and then these last two we also had to change the sign on, since we had to reverse reactants and products. Now, here's the really cool thing about formation reactions and Hess's law. On these reactions, the elements are simply going to cancel out as we try to add up the three reactions. So, look at that. We had 2 carbons on the left side and also 2 carbons on the product side. So those guys will cancel out. If we look at hydrogens, we've got 4 total on the reactant side, and on the product side, each one of the last 2 reactions has 2. So if we add up 2 plus 2, we get 4. So all of the hydrogens are going to cancel out as well. And then last but not least, we have the oxygens, and there's 1 on the reactant side and 1 on the product side. So they simply cancel out. So if we go to add up these 3 reactions, all of the plain elements are gone, and what we have left are simply the 2 things we'd like to see as the reactants and the thing that we'd like to see as the product. When we add together the manipulated delta H's, we end up with a grand total of negative 1,014.4 kilojoules per mole. And if we compare the math that we did in adding up the heats of formation of the reactants and the products, I think you'll be able to see where this granddaddy equation came from. You'll notice that each one of these was multiplied by a coefficient. The middle one had a coefficient of 1. And then the ones that we reversed were the ones that appear on the reactant side, and so we had to change the sign. So let me change colors here to emphasize that. The negative signs that we had to throw out front appear right there. We're changing the sign on anything that appears as a reactant. So we're going, this granddaddy equation is telling us to multiply the coefficients times the heats of formation for all of the products and add that up. And then we're going to do the same thing for the reactants, where we take the coefficients times the heats of formation and add all of that up. And then we're going to subtract the sum for the reactants from the sum for the products. In this video, we found a method for using heats of formation data to calculate the heat of any reaction. We're going to refer to this as the granddaddy equation. And then in the next video, I'm going to work a couple of example problems showing how to actually use that granddaddy equation. Beat 'em up, cats.